Hi everyone, in this video I'm gonna show you a cool derivation, or at least what I thought it was a cool derivation of neural networks from a statistical physics perspective. We're gonna start by trying to define a Hamiltonian of a specific system and then hopefully be able to explain the inner workings of a simple neural network. In order to do this, we're gonna present a really simple problem, which is basically this: a set of points, a set of scattered points in a 2D plane with dimensions x and y. And from what you can see in this diagram, we can see that points that have an x coordinate that is bigger than 0.5, basically this straight line, this yellow straight line, is located at 0.5. So if their x coordinates is greater than 0.5, they're classified as blue, and if it's less than 0.5, they are classified as red. That's pretty much the decision boundary, right? So, as I was saying, it's a very simple problem. It can be described or kind of like showcased with this little diagram here, from which we can see that we can take inputs, x inputs, that would be the x coordinates, and the y inputs, or y coordinates, and then we would come up with this d that can be understood as a label, or um, yeah, pretty much a label, right? It's let's say, for example, if d equals to 1, then the point is blue. If d equals to 0, then the point is red. Um, so yeah, hopefully you have understood this problem statement. I think it's quite straightforward, so we're gonna move on. Um, we're gonna describe the vector that we're gonna have as input as x. Let's write it here. So the x vector is gonna be composed of the x coordinates and the y coordinates, and then we're gonna say that there are two possible labels or outcomes. They're gonna be d equals to 0 and d equals to 1, and um, therefore because d depends on pretty much the input vector x, we're gonna say that um, they seem to be correlated, right? X and d seem to be correlated. So yeah, well, let's just keep that in mind and try to start defining a Hamiltonian. First of all, a quick summary: a Hamiltonian, it's pretty much functional, because it's a function of functions that define a dynamical system in terms of its degrees of freedom, right? So, for example, for a dynamical system with I degrees of freedom, say it has AI degrees of freedom in terms of t, for I equals to 1, 2, however many degrees of freedom it has, right? So, as I was saying, um, the Hamiltonian is gonna be made out of, or composed by these degrees of freedom, basically the AI for I degrees of freedom. Um, if we think about an example, a really simple example, if you have some background in physics, is gonna be the Hamiltonian of the harmonic oscillator, right? So if we substitute, uh, this is gonna have 2 degrees of freedom, the harmonic oscillator. So if we substitute A1 for well, the spatial coordinate, right, and A2 for the momentum, then the Hamiltonian in this case is gonna be this well-known formula. That is a half of the momentum squared plus a half of the position squared as well. This is a quick example of what a Hamiltonian is. Um, we here have that, for example, if the system has two particles, then these two particles behave in an independent manner, then the Hamiltonian is simply just gonna be the sum, right, of the Hamiltonians of each individual particle. So for two particles independent, right? This is important because now we're gonna see what happens if they're not independent. The Hamiltonian is just simply gonna be again the sum of the individual Hamiltonians, right? So P1 is gonna be the momentum of the particle 1, the next one, the position again for particle 1, and well, I'm just gonna put it underneath. Then we have the same, simply changing the subscript of the degrees of freedom to indicate they are of the second particle. Um, okay, so as I'm saying, because they are independent in this case for this last Hamiltonian, then they are not correlated, right? If they are independent, they cannot be correlated. But if we look at another example, for example, we say that there is, for example, a force that acts between the first particle and the second particle. Just a quick diagram. It's going to be particle 1, particle 2. If there is, I don't know, for example, gravity pulling 1 against 2, right? Whatever force X or F, or it can be gravity or electromagnetic or whatever, electromagnetic force or whatever. Then, because there is this force, then we're gonna see how particles 1 and 2 are correlated. In fact, a really common example in nature is that this force, the magnitude of this force, is proportional to the distance between the two particles. So if we introduce this into our system, then we would get an additional term for the Hamiltonian, right? So this would be, let's call it delta H. This would be whatever the constant of proportionality is, let's call it C, times the positional vector of the first particle minus the positional vector of the second particle, because I was saying that they are proportional to the distance between them, and all squared, right? So if we expand these brackets, then we're gonna find that we get two terms first, but what we're really caring about is that we're gonna find something of the form. One of the terms is gonna have the form of the proportionality constant times x1 times x2. So it's basically, this is gonna be a product of the dynamical degrees of freedom of the two particles. So it's important to notice that whenever we're gonna see something of this form, again, the product of two dynamical, or well, the dynamical degrees of freedom of two particles in this case, then this term is what indicates correlation, right, between particles in a system. So, and the strength of this correlation is just going to be determined by again, the proportionality constant, that in fact it has a specific name. Um, this coefficient is called coupling constant. Now, in order to proceed, we're going to have to take a step back to look at, yeah, basically an example in statistical physics, right? We actually want to be able to answer the following question. This question is, given a physical system, right, how can its statistical mechanical behavior be written, right, like expressed in general? So if we look at the classical example that one is given when you are going through the notes of statistical physics, we we know that when a physical system is in contact with like a thermal bath with a temperature T, then the physical system receives energy from the thermal bath, right? There is an exchange of energy, um, and this energy, the distribution of this energy takes the form of the Boltzmann distribution, right? Or as we call it as well in statistical physics, I believe it was canonical distribution, right? So If we want to look more at the equations, the Boltzmann distribution is gonna look, well, basically the probability P, okay, of realizing or finding the energy or the state with energy E. It's gonna be given um, by 1 over z times e to the power of minus e kbt, right? So basically, this set is gonna be the partition function, the well-known partition function that looks like this. It's a sum over all states of e to the power of h minus h Hamiltonian over kbt. Kb is just the Boltzmann constant, E is the energy again, and T is the temperature. Um, this is, well, this comes up to normalize the probability generally, and have the total probability equal to 1. Okay, well, leaving this as an aside, we're gonna see now how it relates to our problem. Let's come back to our our problem here of binary classification of data, and again, because the vector x seems to be correlated with the label d, or the outcome d, let's try to use this information to come up with a Hamiltonian, right? Well, because again we know there's a correlation, then we know the Hamiltonian is gonna take a form like of a form of this, right? Um, it's gonna be the x coordinate times jx plus y times jy plus j, where, yeah, this is simply because well, sorry, where jx, jy, and jx are simply coupling constants, um, that, and we will see that these are going to be the parameters that we really want to optimize for, right? Um, but yeah, this is going to be our Hamiltonian. Um, Now we would like to build a model, right? Let's create a model that we want to optimize and ultimately want to reproduce the true distribution, right? So let's call this model x, q, big Q, and it's gonna be the joint probability of the vector x and d. And we're gonna be using this physical system, right? We're calling it physical because we're using Hamiltonians here. And let's as we were mentioning in the step before, in this little aside we did from statistical physics, we're gonna try to build a Boltzmann distribution about d, sorry. So then our first assumption is gonna be we're gonna wanna start with the probability, right, of d given x, and we're gonna want to explore this distribution because, yeah, then using Bayesian statistics, we're gonna be able to come back to this. So this, as a first step, is gonna look, again, because we're trying to make here a Boltzmann distribution here, it's gonna look like e to the power of the Hamiltonian we came out with just a second ago, and we're just gonna divide it over the partition function, right? Let's expand this a little bit. So we know the Hamiltonian looks like this, and then the partition function, it's just going to be a sum from 0 to 1 of, because those are all the states, it can be either 0 or 1, right, of e. um, let's write it like this with indices, just so we don't have to write all of the degrees of freedom or coordinates, yeah, just for the sake of space, really. And lastly, carrying out this sum. Yeah, I mean we're gonna have the same in the denominator. Sorry, x plus y plus j all times d, and here expanding this sum because let me just because the first d is gonna be 0, we're just gonna get a 1, and then we're just gonna get the basically the same as we have on top, right? This is a script, yeah, and then subscript plus j, which is absolute. Okay, so this is what we sorry, this is what we are finishing with. And this, if one has a bit of background in deep learning, might be able to recognize this. It's actually a sigmoid function, right? The sigmoid function, what a weird sigma though, can be described as well, by definition is just 1 over e to the power of e to the minus x plus 1, and we can see this coincides, right? So just evaluating q of the given x, we can come up, like, because we're just looking at a binary classification problem, we can afford to do this, right? So for d equal to 1, right, let's put it here. So q of j, d equals to, let me put it in capital because this is the parameter. So when d equals to 1, given the vector x, we get the sigmoid, because yeah, I mean, just evaluating the previous, right, and substituting x for the Hamiltonian, we're gonna get the sigmoid times the Hamiltonian y plus j. This is for let me just fix that weird looking j, and then the case for d equals to 0 given the vector x, this is gonna be 1 actually minus the same as above. So x jx plus y jy plus j. Okay, so yeah, I mean this expression is for a given x, but if we really suppose the existence of like data generation probability, right? Data generation probability, that would be like the joint probability of the vector x and d would be like, yeah, basically this data generation probability would be we have some space here, yeah, so it would be the joint probability of x and d. This is a vector again. uh, then the x should be generated according to p of x being equal, we want this to be the absolute probability, right? So the 0 and the same, but when d is equal to 1. So we can use this to define, use this and Bayesian statistics. We can, again, as I was saying before, we can go back to what we initially wanted. Basically our model, that is the distribution, the joint probability of x and d. So for our model qj, d given x times the probability of x. So now we would arrive to the stage of actually learning, right? To be able to optimize for the coupling constants and be able to get um, as close of a distribution to the real one, right? We want to um, indeed uh, make, I mean, ideally we would make p of xd equal to qj, capital J, xd. But obviously on practice this is just going to be approximation, right? But we want this approximation to be as accurate as possible. So for this we're going to optimize for the parameter in Q, that is J, right? The coupling constants. Um, so in order to do this, we have to get a measure of the distance between the distributions, and this is usually done um, with relative entropy, and this by definition basically is just gonna measure the distance between our distributions here, and by definition is gonna be the sum probability, the joint probability of x and d. Again, I might be forgetting to put x as a vector many times, but yeah, x is a vector in this case, times the logarithm of the probability of d given a specific vector x over our model qj d given again an input x. Uh, if we expand this, we're really just interested in optimizing for j again, so we're just gonna focus on terms that actually are dependent on j. So this is gonna be again true distribution times the logarithm of our model 1 d is given um, for a given x, right? Plus, some other terms that we don't really care about because they are independent of j. And here we would use the gradient descent method, actually a stochastic gradient descent method that we talked about in the previous video. So I'm just gonna skip um, you know those steps that actually I went through in the previous videos, and we would get um, the approximate solution, right? There it would be the sum of I to all the data of 1 over n. Big N is just gonna be like the amount of data that we have, right? Times the logarithm of our model for the specific d, right? This is we're just indexing, saying we can imagine d as an array, right, of many data points and of many labels corresponding to many data points, and we're just scripting I. Um, given the vector x, sorry, for in the position I. And doing some rearranging, we can come take this out because it's the constant uh, data, whatever. And yeah, because there are only two outcomes, right? And we know the solutions for these outcomes. This right here are the solutions. We can just simply substitute in plug these um, expressions in, right? Again, benefits of evaluating binary classification. It's quite simple if you compare it. So doing that, we're gonna get, di log. It's not it's not really gonna fit here, but well, let's just say h, right? Because this in the end is gonna be just a Hamiltonian. Let me hold up. I was forgetting about sigma, but don't forget about the sigma activation function. And this is we're just gonna add it to the other outcome. This would be when d equals to 0. So the one we just wrote, this one is for d equals to 1, and now we're gonna write the one for d equals to 0. Okay, log of 1 minus sigma h, right? And again, remember what h is. Um, it contains too many brackets. I might have screwed up there a little bit, but h, as I was saying, it contains the coupling constants and the parameters we're trying to optimize here. So yeah, this would be the stochastic gradient descent method, right? We just used it here, and but ideally, what we really want is just optimize these parameters j, um, by learning, quote unquote learning. Um, but we need a measure to be able to like determine if these parameters are good at this point, or we should still keep going, and this is gonna be typically the loss, right? But for a set of given j's, we can actually make the model, our model, evaluate for a given input x, right? um, in any step. So let's do that. That would be the expectation, right, for a given set of j's and a given parameter. This would look like the following. So it would be for all of the states of d, and then qj d x I. Okay, sorry, I had just forgotten the formula because I'm doing this on top of my head, and yeah, sorry, sorry about that. So it would be our distribution, right, for the real label given, uh, you know, the specific input, and then this would evaluate to qj, capital J again, keep forgetting, of d equals to 1, because if d equals to 0, then everything goes to 0. For a given input, again, and this would ultimately look like the sigmoid function. My sigmas today are looking terrible. For the input plus, this time it's not a vector though, because it's just the x coordinate, right? And we're gonna do the same for the y coordinate. So yeah, this is what we would have in the end, and this would be the output value, right? So knowing what the output value from our model would be at a specific step in training, and for a specific set of j parameters in this case, and for a specific input, we want to evaluate if this this output is correct or not, and we want to come up with a loss, right? In deep learning and machine learning, it's a common practice to come up with a loss. So we're gonna use the cross entropy here. So the cross entropy by definition is gonna be d log x plus 1 minus d log 1 minus x. It's a very common loss function that is used always for this type of problem, and we want to minimize this error, right? Because if the error is 0, then obviously the model is always making the right predictions. And I mean, how do we minimize this, right? Again, we minimize this by adjusting the parameters jx, jy, and j using the gradient method, the stochastic gradient descent, and we would do this for each item in the dataset, right? So for each xi, for I being from I would go from like the first item to the last one for n data points. And yeah, I mean, since deep learning uses the stochastic gradient descent method, sorry, it is actually necessary to calculate the gradient of this error function, like the the cross entropy, with respect to the parameters j. But yeah, this is pretty much it. We, again, starting from a very simple problem and using some techniques and some points of view from statistical physics, we managed to derive things like the activation function, that in this case was the sigmoid, because we're doing binary classification. We saw how we would use the gradient descent method for optimizing parameters, which we should note that in this case was really easy because it's just as well just a one layer network that we're using here. But for future videos I will go through the work of doing it for like a deep neural network. But there are different methods that are used. Then we managed to evaluate an output for a given input in our neural network for a specific step of the training. That will be this, and then using this output in loss function to like compute the error and then minimize this error. But yeah, I hope I managed to explain myself clearly. This is the first. This is one of the first videos that I do, kind of showcasing a derivation and going through it, explaining it step by step. But yeah, I would appreciate any feedback you have, and um, yeah, see you in future videos. Bye bye.